Hello everybody, let us start lecture 2. This is the second lecture and today we will cover two topics. One is information obtained from phase diagram, what kinds of information or idea what we can get from phase diagram, and the second one is definition of important terms. And this definition of important terms will cover few things and then we will cover more in our subsequent lectures. Now, let us look at the information what we can get from phase diagram. If you look at our first lecture, which is the introduction lecture, we have talked about the definition of phase diagram, and then we have also given example of single component phase diagram, and we have given example of water, and also we have given example of copper nickel system, which is isomorphous, and where we have phase boundaries, and then we have zones marked as phase, and we could also sense that each phase that appears in a system is a function of system variables, and the phase which is more stable as per that system variables would be existing in the phase diagram. Now, we have to see what are the other informations what we can get out of it. In fact, in the previous lecture we actually sensed that some of the informations like fraction of phases, phase zones, and where we can get two phase equilibrium, where we can get single phase existence, like that we could get. But let me just list those informations or informations what we can obtain from phase diagram. So, one is definitely, if I try to look at the information, one is change of phase, and that actually indicates phase transformation, and while doing that, while understanding phase transformation, we can also see it is a function of system variables like pressure, temperature, composition. Okay. Those are the system variables. Okay. Then the second one, we can see the condition of phase. What do you mean by condition of phase? Like its physical appearance, like solid, liquid, vapor. Those are the physical appearance what we can get of a particular phase appearing in a phase diagram. Now, then we can also check the factors deciding change of phase, actually that is indicated in the first thing. So, then we can get composition of a phase. For a single component system, composition does not come into picture, but for multi-component system, composition does, it has to be mentioned, otherwise we cannot reach to a point in a phase diagram. In case of isomorphous system, we have seen that each point in between the pure metals like pure copper and pure nickel, we have a specific percentage of nickel and specific percentage of copper. And when we see the phase transformation in case of single component system, composition does not change, the state or the condition of that particular, the physical appearance of that particular phase changes. Like in case of water, we could see that it can go to liquid to solid or solid to liquid if we keep the pressure constant and change the temperature. If we increase the temperature, it can land up in liquid zone from the solid, and if we decrease the temperature, definitely liquid will turn up to solid as at a constant pressure. Okay. So, in the single component system, we see only the phase that change of appearance. Okay. But in case of binary system, since we have talked about binary system, we could see that whenever the phase transformation happens and the phase diagram what we have talked about, which is basically isomorphous, that phase diagram has pressure constant, all the time the pressure is kept constant. So, the variables what we are bothered about, we are actually considering, one is temperature on the y axis and x axis we take it as a composition, and we see that whenever a liquid, a single phase zone, which is also a kind of appearance as liquid, it moves to the two phase zone, which is basically the in between the eye of that isomorphous. There we could see that two things come up, one is liquid, another one is solid, but that two phases would have a definite compositions of nickel as well as copper. Okay. So, for example, let me just explain this one little bit. For example, if we consider the single phase we consider temperature and pressure, and in case of water the schematic diagram is like this. This point where all the lines meet at a point, that point is called triple point, and we have given example like this. Let us say this is called melting, and the back transformation is called solidification, and that time we are keeping the pressure constant and we are changing the temperature. So, composition still it is one component. So, but you know it changes from liquid to solid and solid to liquid. But in case of binary system, the example what we have seen in the last lecture, percentage of nickel we are changing, this is 100% nickel and this is 100% copper. So, here it is copper melting point and this part is melting point of nickel, and melting point of nickel is more than melting point of copper, and the diagram looks like this. Okay. And we have taken a composition like this. Here if we consider which is purely liquid, and as we go and reach there, the first solid appears which is rich in nickel and rest of the thing will be liquid. In between we have rich in nickel solid and rich in copper liquid. This is liquid, this is solid. Similarly, once we reach here, so then this will be liquid rich in copper and this will be solid of the same composition, which is nickel. This is solid, this is solid. So, now you could see that, and if we reach to this place, it will be entirely solid. But every time as we go through that I portion, we see that the transformation is taking place, two phases are appearing and those two phases will have different compositions. So, that means we can get composition of the phase as well as physical appearance of that phase. Here liquid and solid only, but in case of single component system, as we go from liquid solid equilibrium line to liquid vapor or solid vapor, we can get transformation between liquid to vapor or solid to vapor. So, there only the physical appearance changes. So, in fact, I can add to this, I can also get the information about physical appearance of a phase. Okay. So, we can get those informations, and the last one is we can also get fraction of different phases. Okay. And fraction of different phases when we talk about, if it is single component, on a single phase zone it is 100% solid or 100% liquid. Similarly, in case of binary, on a single phase point like this point or this point, everything will be either liquid or solid. And if I try to look at these points, the points over solid liquid equilibrium line. Okay. So, in case of single component system, at the equilibrium line, if we consider any point, we cannot get to know the fraction of it. Okay. That is the fundamental concept of thermodynamics. We will talk about it when we talk about the free energy factor as a when we talk about phase transformation and what is about free energy change during phase transformation. That time we will try to understand why at the equilibrium line, any point we consider, we cannot get any fraction. So, if we do not get any fraction at the equilibrium line, then we get one information correct, that is liquid and solid both will be under equilibrium, but we cannot get any fraction. But that is not true in case of binary system. We do get certain amount of change, okay, and that change we can quantify. That change means that fraction of phase that appears, that we can quantify, okay, and that quantification comes from lever rule. So, we will talk about lever rule as we go ahead when we talk about binary phase diagrams. So, fraction of different phases, if it is single component, in single phase region, it is all the time 100% of that particular phase. Okay. But in case of binary phase diagram, we do get fraction calculation, fraction of phases with the help of lever rule. Okay. Now, this lever rule will be taught later. So, at least we can get the fraction of different phases. So, these are the informations we get, and we can get several other informations, like if we have a little prior idea of a kind of phase crystal structure, okay, we can get the crystal structure of a phase. We can get that. Okay. In fact, crystal structure part will come into our consideration when we try to understand solution thermodynamics, and using that we can calculate. There are two regime we will consider. One is ideal solution approach, another one is regular solution approach. In the regular solution approach, we have to consider crystal structure part. Okay. So, that time you will see that the crystal structure of a phase can also be obtained from phase diagram. Okay. So, and also depending on the crystal structure, we can get different other informations like invariant reactions informations we can get. Reactions, or we can say invariant point, where a particular reaction, invariant reaction happens, like we can get eutectic, we can get eutectoid, we can get peritectic, okay. Several such reactions we can get. We will learn those systems, but at least you can see that invariant point is where the degree of freedom which is considered as f is 0. Okay. We learned this degree of freedom. This degree of freedom is related to a phase rule. We just touched upon phase rule. Phase rule is decided by C minus P plus 2, and this is in case of non-reacting. It is a kind of generalized phase rule. We will talk about it later for reacting as well as non-reacting systems. Here C is the component P is basically phase or number of phase, and 2 comes from 2 variables, which is pressure and temperature. So, we will talk about it. So, this degree of freedom means this F part. So, this F becomes 0 at those points, invariant points, and there invariant reactions happen. In fact, in case of single component system like water, we have one invariant point where degree of freedom becomes 0, like this point. Okay. Let us see whether degree of freedom can get 0. For example, if how many phases are coexisting at that point, we talked about it, solid, liquid and vapor. So, phase becomes 3, and how many components? It is a single component system 1, and these 2 parts are coming, which is pressure and temperatures 2. So, you see it becomes 0. So, that point is unique point at if we have that at the fixed pressure and temperature only we can get those 3 phase equilibrium. Okay. So, we will talk more about that, but at least we can get to know those invariant reactions. Okay. So, this eutectoid, eutectic, peritectic, those appear in case of binary systems, since our discussion is only on the binary phase diagrams. So, you will see that how those reaction happens and how to get those reactions using fundamental aspects of thermodynamics, and in fact, we will talk about free energy composition diagram, and from there we can actually calculate phase diagram. We can draw phase diagram, and our understanding about phase diagram will be further enhanced. Okay. So, these are the information we can get. We will get lot more as we go ahead. We will see how the information window opens up. Okay. So, now, so fine, we get those information. So what? So, it has to be beneficial to the material scientists or materials engineers. So, how those become beneficials? Okay, let us look at it. Okay. So, benefits of or usefulness of phase diagram. In fact, this stems from the information what we get from phase diagram. So, it can lead to a kind of road map for new material development. Like new alloy. Okay. I am just giving an example, new ceramic composite, we can get many information, many such developments like that. Okay. We can actually, this actually leads to a new material design. So, for example, like aerospace applications, creep resistant applications, we consider nickel based superalloys, and where we add titanium or aluminum, we get Ni3Ti, that is a phase. That phase, if it appears in a system, it actually improves the creep resistance, because that phase has a higher melting point, okay, compared to other things that are appearing in the system. So, that higher melting point substance can give you higher creep resistance. So, kind of new material design we can also think of by looking at the phase diagram only. Okay. So, now then we can also look at the process optimization. So, process optimization, the phase diagram gives us certain information, certain kind of help, but it has to be combined with another important aspect, which is called kinetics, because phase diagram is based on thermodynamic principles. So, that means it talks about feasibility of a phase appearing in a system, but actually whether that phase would appear or not, that would be decided by the kinetic factors, the rate at which that phase forms. So, phase diagram does not give you that information, that what is the kinetics of it, of the kinetics of a phase transformations. So, since it lacks, if I try to see the lack of the phase diagram, where it lacks actually, it does not give you the phase diagram does not give kinetic information. So, this is a kind of lacking part, but at least when I talk about this process optimization. So, when we talk about process optimization, that means I am talking about processing. And the processing, whenever we talk about processing, one particular processing that comes into our mind, which is called heat treatment, which is basically a function of temperature, pressure, temperature, stress as well as time. Okay. So, heat treatment optimization can be our tool to make an alloy system or kind of a ceramic system much more useful for a particular application. Okay. So, that can also we can get, but we get a partial information, but we, since it lacks kinetic information, we can get complete idea of that process optimization if we consider kinetics along with the phase diagram. Okay. So, but at least still we get kind of idea. Then we can get desired microstructures. At least the fraction of phases, and also what would appear first, what phase would appear first. For example, if I look at this binary phase diagram, if I come from top to bottom, we can see that the first phase that appears in liquid will be solid and that will be richer in nickel. So, that information I can get. Okay. So, that means I can see that I can get desired microstructure, how much fraction of different phases I would need, that I can actually get it. But again, since the phase diagram lacks the kinetic information, so we get a partial information, but that information would be very vital. So, that kinetic factor will be also dependent on that particular information. So, desired microstructure we can also get. Okay. Property prediction. Since we know what microstructure it would form, and then each phase has a particular property, like for example, if I consider iron carbon diagram, if we consider low carbon composition, let us say 0.01% carbon. So, which is basically falling in the category of IF steel, interstitial free steel, if we reduce nickel as well as carbon. And then we can have a kind of material which will be very soft, but at the same time this has a huge advantage for making a sheet metal, and there since we can get almost about 50% deformation in that particular material. So, material becomes very soft because there we get predominantly ferrite. Ferrite is a soft phase with a low carbon, and there is another phase that can appear, but that appearance would be so low, that carbide which is called cementite, that will be so low. So, we can say insignificant presence, and that would give us a kind of microstructure which will be completely ferritic, okay, and it has a very high level of deformation ability. So, now you can see that by looking at the phase transformation, what phase appears, what will be the possible microstructure, we can also predict the property to some extent. Okay. Of course, when there would be complications, and that complication would definitely change the properties, but at least it actually gives an idea what should be our property in the new alloy that is developed. Okay. And once we know all this, definitely it will actually give us a kind of idea of performance. Since finally, whenever we are actually making an alloy for certain applications, its performance needs to be looked at. It should be durable, it should provide a good level of workability, it should give us a good level of protection, it should give us a good level of stress bearing property. All those performance we can look at by looking at other things. Okay. So, that means you could see that phase diagram has a huge importance in materials development, designing, process optimization, desired microstructure development, property prediction and performance. In fact, if we see phase diagram, it actually falls within the gamut of materials tetrahedron. So, we know materials tetrahedron. So, materials tetrahedron is basically, it talks about a kind of diamond where we have here structure, then properties, then structure can be atomic or microstructure or macrostructures. Then we have properties, then performance, and of course, one side would be processing. So, there is one more aspect which is composition. Okay. So, that composition can also be built in with this particular materials tetrahedron, and you see whatever we have discussed that falls within this material tetrahedron thing. Okay. So, that means it is very clear that phase diagram gives a lot of informations and lot of idea for the next level of development. So, now once we learn this, let us look at some of the variables. So, now we have seen that phase diagram, if I need to understand it, we have to understand thermodynamics, and in order to understand thermodynamics, we also need to understand some of the parameters which or the laws on which the thermodynamics are constructed. Okay. So, let us look at some of the variables or the you can say terms, thermodynamic terms, before we get to thermodynamic concepts. Okay. So, now or the laws. So, let us look at some of the important terms. If we look at the definition, very definition of phase diagram, we said that it is a kind of graphical representation of stability of different phases appearing in a system as a function of system variables. So, that means the first thing that comes up in our mind is basically phases, phase. So, how do we define phase? Okay. So, phase can be defined as is a kind of classical definition, compositionally homogeneous, physically distinct, part of a system surrounded by a boundary. Okay. So, this is a basic classical definition of phase, compositionally homogeneous, physically distinct part of a system surrounded by a boundary. So, let us understand this. Okay. So, if we talk about a kind of let us say if we have let us say oil and water. Okay. So, this oil and water if you see, and if we let us say this is a closed system, this is the oil part and this is the water part, and we know that oil floats on water, and in fact, there will be some vapor also. Okay. So, in fact, we can say that this oil part is quite distinctly visible, and in the oil part at every point if you look at a kind of similar composition will be noticed, and in the water also if we look at, we will see almost similar type of composition, and there will be also a vapor phase which will be lying here. Okay. So, that vapor also is, though it is not visible, but at least there are vapor molecules. So, now you can see that all the three phases are there in this particular system, closed system. Okay. And of course, it will have some pressure and temperature, fine. So, since it is a closed system and the pressure and temperature are also there, and why I am saying the phase, here I am defining the phase. Now, water is a particular phase, oil is a particular phase, and vapor is also a particular phase. Now, if I try to look at a system, let us say a open system where I have water and I put a ice in the water, ice will be floating. So, now I can check the ice, actually I can actually physically distinctively I can see that, and in the ice if we look at, every point more or less would have a homogeneous composition. Okay. And this is ice, this is water. Water means whenever I am talking about water, it means that it is a liquid phase, is a liquid water, and of course, there will be vapor also. So, you can see that everything is physically distinct, and in a particular entity which is ice, that ice has a similar composition everywhere, and there is a boundary also. So, ice boundary and water boundary is clearly visible. Okay. So, that means the ice can be considered as a phase, liquid water can be considered as a phase. So, this is the concept of phase. So, phase we will go ahead and then learn more about this phase. So, phase can be single component, phase can be two component, phase can have different compositions, but different composition, that does not mean that everywhere the composition is changing. Okay. So, if the compositions are changing constantly and a dynamic process, then we will not consider it to be a kind of phase, because that time it is a dynamic process. Once it becomes stable, that means once it achieves equilibrium, then the phase entity becomes very easy to absorb. Now, the second part when we talk about system. Okay. When we talk about system, system is again can be considered as part of an universe by a boundary. Okay. In a system we can have multiple phases, in a system we can have single phase, but again this will be basically a part of an universe which is separated by a boundary. Simple definition. Okay. But if we try to look at the complicated part, if a system, basically whenever we talk about the part, that means it is a kind of, I am looking at the quantity of matter or material, fine. Okay. So, that is separated from the universe, okay, from an universe. So, I can in fact I can put it as a D from the universe. Okay. So, now if I talk about this is a system, then outside would be surrounding, fine, and the system is actually separated from surrounding with the help of a boundary, and system plus surrounding, it constitutes universe, fine. Now, this boundary we have to define. So, this boundary there could be different boundary. So, the boundary could be, one is, let us say I can consider it to be diathermal boundary, okay. I can take it as a adiabatic boundary, okay. So, I can sense that adiabatic boundary, I can say that it does not allow mass to pass through, but it does not allow, let me just change this, does not allow heat as well as mass to pass through. In diathermal wall, it allows heat flow, but does not allow mass flow, fine. So, these two boundaries are there, and depending on the existence of these boundaries, I can define different systems. Like I can think of a kind of closed system with a boundary, and in a closed system definitely it does not allow mass to flow out, but closed system can have a adiabatic boundary. So, that means it does not allow heat to flow, but it can also have diathermal boundary which can allow the heat to flow. So, in case of adiabatic, heat does not flow, and in case of diathermal, heat can flow in and out from the system. Okay. So, I can have closed system. So, closed system definitely does not allow mass flow. It can allow heat flow depending on whether the boundary is diathermal, is diathermal, and it cannot allow heat flow, that time it will be adiabatic well, adiabatic. And there is a system called isolated system. So, it actually does not, again it does not allow any mass or heat flow, okay. And there could be a system called closed open system. So, it is a completely isolated from rest of the universe, from the rest. Let me just put from rest. An open system, it allows heat as well as mass through and out of the system. Okay. So, let us stop here. We will continue our discussion on definition of different phases, and then finally, we start correlating different systems, as well as now we will talk about variables or the properties of the system, and then our discussion pattern will change to understand those variables and how to define system with the help of those variables. And interestingly, we will get to know that our variable choice will be such that we should be able to measure those variables experimentally, so that the system can be defined experimentally. Okay. So, let me stop here. We will continue our lectures in our subsequent sessions. Thank you.